Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing developments in science and technology that are going to touch our lives and affect human destiny. And if you've been following the news, you know that Elon Musk, the visionary behind SpaceX, many people compare him to Tony Stark, the man behind the Iron Man comic book series. Many people think that Elon Musk is prophetic in terms of talking about cities on Mars. That's right. Forget about putting an astronaut on Mars. We're talking about putting a city on Mars with 1 million inhabitants. An incredible press conference that is already generating a tremendous amount of excitement and some skepticism. First of all, in 2 years, he wants to send the first unmanned rocket from SpaceX to the planet Mars. 2018, the first unmanned mission to the red planet. And then 2024, hold on to your hats. 2024, he wants to send the first manned mission to the red planet, beating NASA by perhaps 10 years. NASA hopes that perhaps by the early 2030s, it may have a mission to Mars, maybe orbiting around Mars, and actually landing on Mars perhaps in the 2040s. Well, Elon Musk says that private enterprise and ingenuity and individualism, he can actually beat NASA's time frame. This is potentially amazing. And then he envisions perhaps sending 1 million colonists and tourists to the red planet. He envisions having 1,000 Mars ships in orbit, each one containing 100 colonists, to begin the process of creating a multi-planet species. In other words, it's too dangerous, he says, to put humanity in one basket because, for example, asteroid strikes, global warming, rampant biogerms, whatever, can wipe out humanity. It's simply too dangerous. We need an insurance policy. We have to put astronauts on at least 2 planets, maybe more. And he wants to be the man to do it. In fact, that's one of the reasons why he created SpaceX, which has already revolutionized space travel by introducing the reusable rocket. He wants to reduce the cost of space travel by perhaps a factor of 10. So instead of costing $10,000 a pound to put anything in near Earth orbit, it may cost $1,000 a pound to put anything in near Earth orbit, which could literally open up the heavens for commercial space travel. So is it outlandish? What's the catch? Well, there is one small catch. Actually, 2. First of all, it is dangerous. He publicly admits that, yes, people will die. Let's get used to that fact that there is something called the Mars jinx. Something on the order of 30-40% of our space probes really never make it to the red planet. But more important is cost. That 4-letter word, cost, C-O-S-T, it'll cost about $10 billion to send the first of these missions to the red planet. Eventually, the cost per passenger will be down to about $200,000. Imagine, $200,000 per person to go and visit the red planet. And of course, he's a realist. He says it'll take a public-private consortium. In other words, even he, the billionaire, does not have enough money to single-handedly fund this manned mission to the red planet all by himself. It'll be a combination of public and private funding. But already he's revolutionized our understanding of space travel by reducing the cost, by making reusable rockets part of the inventory of the space age. So, hold on to your hats. Perhaps by 2024, we will see humans on the red planet. Amazing. Well, once again, we're going to introduce our 2 special guests today. The book is called Beyond Earth, Our Path to a New Home in the Planets by Charles Walford and Amanda Hendricks. Find out about what it means to blast off to Mars and even Titan, a moon of Saturn, in this edition of Science Fantastic.
This is Science Fantastic. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're going to talk about exploring the solar system in a way that you've never heard before. Perhaps you heard the statements from Elon Musk talking about the colonization of Mars. So we're not talking about the moon. We're not talking about the space station. We're talking about going to the planets. What's out there beyond the moon? What about Mars? Is it possible that one day we'll have a colony on Mars? Or for that matter, what about the other planets, all the way going out to Saturn and maybe even Titan? With us today, we have two distinguished guests, author of a new book, Beyond Earth, Our Path to a New Home in the Planets. We have with us Charles Walworth. He's the author of 10 books, hosts a weekly interview program for Alaska Public Radio. And we also have Dr. Amanda Hendricks, a planetary scientist who's worked 12 years for NASA's Propulsion Laboratory. So Charles and Amanda, glad you could be on Science Fantastic.
Thank you.
Thanks for having us.
Okay, Charles, well, the first question for you, the question that we always ask our guests is, how did you as a youth first get interested in science and in your field also journalism?
Well, I guess beginning in science for me was all about kind of the natural environment. I grew up in Alaska, so it was tide pools and outdoors, and this is something that made this project interesting for Amanda and I, because she's very much a space scientist, and I came more from an environmental background, so it gave us two different perspectives on this topic of moving, to another planet. In terms of science writing, I was deeply involved in reporting on the Exxon Valdez oil spill in Alaska, which turned out to be a really big science topic. And so that made me realize that science was really, the scientific viewpoint on the world was really a great avenue to truth and to writing fascinating, important topics.
Okay. And Amanda, how did you get started being interested in science?
Well, for me, it started in school. When I was in second or third grade and we learned about the solar system at school, I fell in love with the topic, and I decided I loved the planets. And at around the same time, the first Viking lander landed on Mars, and so we had the first images of another planet taken from that planet, and showed us the landscape of Mars, and that was it for me. I was done.
Okay.
And so from that point, I decided I wanted to do something involving the planets and space for the rest of my life.
Okay. Now, Charles, you probably heard the big news. Elon Musk, who's been compared to Howard Hughes and to Tony Stark of science fiction fame, has announced a rather ambitious program to explore not just the moon, but to go way past the moon onto Mars. So let's break it down for a moment, okay? Where are we in the space program today? And do you think that it is reasonable that we can begin the possibility of sending, well, in his case, space tourists to Mars? What are your thoughts?
Well, I definitely think we need to be working on it, but there are some really huge challenges to getting people there that are in the way, and that NASA and all the space community needs to do concentrating on much harder, having to do with the galactic cosmic rays and the impact of that radiation on human health. One thing that we looked at was that there really there's too big of a health risk at this point to going to Mars without some substantial science breakthroughs to get there faster, so that radiation exposure is not as long, both in terms of cancer risk and in terms of cognitive impacts on the brain of these large ions coming from the cosmic galactic rays. So that's something that we studied hard in the book. We wanted to write in Beyond Earth very realistically. We didn't want to just imagine what could happen. We wanted to document what was really possible. And at this point, I think Elon Musk is probably overreaching, because I don't think that he could get 1 million people there, but I don't think he could get them there healthy or stay healthy until there's some breakthroughs.
Okay. Amanda, there are some deniers who deny that we even been to the moon. And these so-called skeptics say that, well, surrounding the Earth there's a Van Allen belt, which is quite radioactive and dangerous. And there's no way that our astronauts could have gone through the Van Allen belt to the moon. Well, forget the Van Allen belt. We're talking about Mars now. So tell us, how dangerous is it in outer space about the Van Allen belt? And I understand that cosmic rays are so plentiful out there that even in the eyeball, that you can actually see flickers of light in your eyeball because of cosmic rays that go through the fluid in your eye. Could you elaborate?
Right. So that has been seen since the first days of sending humans into space, that there have been vision issues that only recently on space station has begun to be more thoroughly studied. And, you know, the true aspect of the problem has been realized. And that has to do with radiation from the sun, but as Charles was pointing out, the even more dangerous radiation is the stuff that is really difficult to shield from, and that's the galactic cosmic rays. If I can go back to the Elon Musk thing, though, I would say that it's really terrific in a lot of ways that he is doing this whole program, because if we want to send humans to other planets, NASA can't do it alone, and even all of the space administrations from all the different countries can't really do it alone. So it's really important that nowadays the commercial industry is getting so involved. So I think it's really great. However, again, there are significant health risks that need to be addressed if we want people to get to Mars or other planets and then survive there for a long period of time. Elon himself, I think, acknowledged that there's going to be a lot of deaths along the way. And that's certain to be true, but you do have to start somewhere. And so I'm feeling somewhat positive about his whole plan in a lot of ways.
Okay. Now, Charles, it's always great to see our astronauts spinning upside down and waving at us under weightlessness. But weightlessness has a downside, too, right? I mean, the Russian astronauts, Commander Polyakov, after spending over a year in outer space, when he came down, he had to crawl like a worm. There was so much muscle atrophy that he couldn't even walk. Could you elaborate about the problems of weightlessness?
Yeah, one of the several astronauts we interviewed, Mike Barrett, described coming back to Earth as being a refrigerator magnet. You just felt like the Earth was cranking you down with its gravity. And that has many physiological effects. NASA has done a good job of doing countermeasures on some of them that were most obvious, including the loss of muscle mass and the loss of bone density, which are pretty serious and happen pretty quickly in space, just because you don't have the resistance of gravity to help those cells build while you're, as they do on Earth. But what has been discovered more recently is this thing that Amanda mentioned, which is pressure in the eye, the intracranial pressure, which is caused by your cerebral fluid building up in the head and not circulating normally, appears to damage or cause impact on the optic nerve, which after a certain amount of time could be irreversible and cause blindness. And that's something that's been a big concern for the last few years for NASA and really has not been solved. The only clear solution to it would be either get there quickly so that the damage doesn't become too severe, or use artificial gravity with some sort of centrifugal motion on the spacecraft so that you have the effect of gravity causing your cerebral fluid to continue circulating. So that's one of these major health issues that has to be resolved, and it's probably not impossible to resolve, but it will require more investment and more concentrated effort, which I think Amanda and I really feel would be help created by a goal like space colonization, which is what we address in Beyond Earth, our book.
And Amanda, as was mentioned by Charles, you can spin the spacecraft, giving you artificial gravity. But if you use Newton's laws of motion and do a back-of-the-envelope calculation, you would have to have a rather expensive spacecraft. It would have to be rather large, and spinning it would be impractical. Or what are your thoughts? You think that at some point in the future we may be able to solve the problem of weightlessness?
Yes, I think that, and we spoke with a couple of experts on this topic, structures and artificial gravity for beyond Earth in our research, and I think it's certainly doable and absolutely necessary, as Charles points out, for health concerns. But it will be complicated. It is a non-trivial problem, but you can, just like in the old days of science fiction, you can create. For instance, a wheel-shaped spacecraft that's spinning at a certain rate. It depends on how big it is and how much gravity you want to create. That all depends on how fast you want to spin it, and that depends on structural integrity and so forth. So there's a lot of different components that go in. You can make a spacecraft where part of it is spinning. And so there's a lot of different ways to do it, and it's complicated and it does get expensive, but it is necessary. And people are really thinking about this. This is going to be the way that it's done. I'm convinced of it.
Okay, now Charles, going to the moon was actually like a cakewalk. I mean, just 3 days and you're on the moon for our astronauts back in the late 60s and 70s. However, tell us a little bit about how long it's going to take to go to Mars. And in that time, we have to deal with micrometeorites, accidents, and not to mention the psychological dimension of being cooped up for months with people that you may not particularly care for. What are your thoughts?
Well, the distance between the Earth and Mars varies greatly, and the speed of the spacecraft we're able to build will obviously be a determinant too. Probably like a 9-month trip to Mars is reasonable, and then the time you spend on Mars and the time to get back, and that's probably beyond our capabilities now in terms of keeping the astronauts healthy, as we mentioned before. But there's a lot of things that can be done to make it to bring it closer to our capabilities. I think that faster spacecraft and innovative propulsion will help. There's some really fascinating research going on having to do with food and how to provide palatable food that will last long enough in that environment, which is
okay. Charles, we have to take a short commercial break, but after the break, we're going to continue a discussion of the colonization of Mars. Forget the moon. We're talking about Mars. We're talking about Titan. We're talking about exploring the solar system with Charles Walford and Amanda Hendricks, and the book is called Beyond Earth, Our Path to a New Home in the Planets. And you are listening to Science Fantastic.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. With us today is Charles Walford and Amanda Hendricks. And the book we're talking about is Beyond Earth, Our Path to a New Home in the Planets. And as you probably heard, Elon Musk, the driving force, the billionaire behind SpaceX, has laid out a roadmap by which we can begin to put cities, not just astronauts. Forget that. We're way beyond that. We're talking about cities on Mars. We're talking about perhaps 1,000 starships, 1,000 interplanetary ships with perhaps 100 tourists on each one, potential colonists beginning the process of colonizing Mars. Well, let's bring it back down to Earth. Once again, we have Charles Walford. He hosts a weekly interview program for Alaska Public Radio. And we have Dr. Amanda Hendricks, planetary scientist, and has worked 12 years at NASA's Propulsion Laboratory. So, Charles, let's break it down now. Elon Musk laid out a time frame, 2 years. He expects a modified Falcon rocket, an unmanned rocket, to reach Mars. And then by 2024, perhaps 10 years before NASA, he wants the first ship a manned ship to go to Mars, and eventually envisioning 1,000 such ships, each ship containing 100, colonists to go to Mars. Let's break it down. First of all, do you think it is reasonable, the time frame that he mentioned, 2024, to send the first manned mission to Mars, beating NASA by perhaps 10 years?
Well, I mean, it's hard. You don't want to bet against Elon Musk. He's accomplished some extraordinary things with SpaceX and with Tesla and with Solar City. But also, if you look at his record, he tends to predict things are going to happen a little bit quicker than they actually do, because the technical challenges of building rockets and of making these extraordinary leaps are very, very high. The thing that we found in working on Beyond Earth was that Musk has really figured out how to innovate in a way that NASA doesn't know how to do or has forgotten how to do. We went to his plant and met with one of his engineers, and they really have a kind of Silicon Valley agile innovation culture there, where they're able to make advances very, very quickly and implement them without the bureaucracy that's found at NASA. So if anybody can do it, I think it's Musk. But I think that, as we said in the first segment, there are some real issues in terms of keeping the passengers healthy, which will take some very important basic research that really can't be rushed.
Okay. Now, Amanda, let's talk about the science of being on Mars. First of all, the air. Tell us a little bit about the carbon dioxide atmosphere and how cold it is. It is, of course, a frozen planet, the planet Mars. And what it would be like for an astronaut to build the first manned space station, a base on Mars. Tell us a bit about what it's like to live on Mars.
Well, Mars is an interesting planet. It would be, to live on Mars, I would think, would be maybe okay for kind of a while. It's cold there. There's not much atmosphere at all, and it's certainly not a breathable atmosphere. And it's not a very thick atmosphere. So astronauts, colonists would have to wear pressure suits. They would have to bring their own oxygen, of course, to breathe. And they would need habitat that would keep them safe from micrometeoroid bombardment and from radiation, and would give them kind of a stable temperature, because there are wide temperature swings between day and night. But some more positive aspects of Mars are that there is water there, of course. At the pole, there are polar caps that have frozen water in them, and there's water in the subsurface, frozen, even down to lower latitudes. So that makes things a little easy in terms of providing water for astronauts and colonists to use for fuel and for building and for drinking.
Okay, well, let's take another short commercial break, and we're going to continue a discussion of what would it take to begin the colonization of Mars. With us today is Charles Walford. He's authored 10 books, hosts a weekly interview program for Alaska Public Radio, and is a winner of the Los Angeles Times Book Prize for Science and Technology. Dr. Amanda Hendricks is a planetary scientist, worked for 12 years for NASA's Propulsion Laboratory, and has appeared on numerous TV programs, and is a principal author of many scientific papers. And the book is called Beyond Earth, Our Path to a New Home in the Planets. And once again, you are listening to Science Fantastic with Professor Michio Kaku. Give us a call and be part of the fun. Give us a call at 866-323-2129. Once again, that's 866-323-2129. And perhaps you can ask your question on over 100 radio stations that carry Science Fantastic. Also, go to my website, mkaku.org, mkaku.org, or go to my Facebook site. We have 3 million fans on Facebook and 500,000 people that get my Twitter feed. And again, the website is mkaku.org, mkaku.org. Well, let's take a short commercial break. And after the break, we're going to talk about building a city on Mars and then beyond Mars, perhaps to Saturn and one of its moons, Titan. So stay tuned as we blast off into outer space.
This is Science Fantastic. This is Science Fantastic.
Welcome Welcome back to Science Fantastic with Professor Michio Kaku. Today we're going to blast off. We're going to go past the moon. We're going to go on to Mars and even beyond Mars. With us today are the authors of a new book called Beyond Earth, Our Path to a New Home in the Planets. Charles Walford and Amanda Hendricks. Charles has authored 10 books, hosts a weekly interview program for Alaska Public Radio, and Dr. Amanda Hendricks is a planetary scientist and worked for 12 years at NASA's Propulsion Laboratory. Charles, you probably saw the movie The Martian, and there's Matt Damon struggling to maintain a little bit of oxygen and enough food to keep him alive for a few weeks. What are your thoughts about the movie? Was it realistic, and did it really portray the difficulty of living on this rather hostile environment called Mars?
Well, obviously different people had different opinions about it. We spoke to some scientists at NASA who thought that there were some issues in the movie that weren't that realistic, especially the way the food production was done, that he probably would not, what he did probably wouldn't have worked in terms of growing the potatoes. The other issue that I don't think is really addressed is the radiation, as we discussed earlier. The shielding that's needed for a long stay on Mars is pretty considerable. You'd probably want to have your habitat underground in order to really survive that radiation long term. So, I think there were, I really enjoyed the movie, and I think sounds like it was a great book with a lot of engineering in it, but I'm not sure that Matt Damon would have made it.
Okay, so Amanda, what are your thoughts? Was it realistic? I mean, if it really happened like that, do you think he would have survived or would have perished for lack of oxygen, lack of food, lack of all sorts of things?
Well, I think he was quite innovative and clever in the techniques that he came up with to get himself out of jams here and there, and it was certainly entertaining. I think overall it was not too far off. The main issue that I had scientifically with it was about the atmosphere and the windstorm that came up. We know that there's dust storms on Mars every so often, but there's just not enough atmosphere to create that much wind, as was portrayed in the film. But it made it more exciting for the movie, that's for sure.
Right.
And of course, I don't think that they were planning on staying there for very long. So I imagine that after coming back to Earth, Matt Damon's character would have suffered from tissue damage and possibly a shortened lifespan due to his accumulated radiation over his longer than planned time on Mars. But certainly any longer-term colonization of Mars would need to plan for some sort of underground habitat to help shield from that radiation.
Okay, well, let's take another short commercial break. Once again, you are listening to Science Fantastic with Professor Michio Kaku.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. With us today are two authors of a new book called Beyond Earth, Our Path to a New Home in the Planets by Charles Walford and Amanda Hendricks. And before we were talking about the colonization of Mars. However, they're more ambitious. They see Mars as a stepping stone to Saturn as we go to Titan, one of the moons of Saturn. So, Charles, why did you say Titan when most science fiction writers and Elon Musk, the billionaire, are concentrating on Mars?
Well, I think that the concentration on Mars is because it's the nearest planet and seems like the easiest to get to. But we started our project in Beyond Earth in looking at where would be the planet that would be easiest to live on, where you could survive with the fewest technological interventions. And that was Titan. It's a moon of Saturn, which has a thick nitrogen atmosphere and has a very plentiful supply of hydrocarbons and water that would allow you to have pretty much unlimited energy supplies. So it gets you through many of the environmental problems you would face on Mars and allows you to think about a society living there permanently, self-sufficiently, without connection to the Earth.
Okay, well, Amanda, Titan has a lot of, I think, what is called ethane, and it is potentially combustible, but it requires oxygen. Therefore, you cannot light a match on Titan in order to burn some of the hydrocarbons there. So is it really possible to harness the fuel on Titan, given the fact there's no oxygen to oxidize the fuel?
Yes, it is. And again, it's not a super straightforward problem, but there is water on Titan. As a matter of fact, it's made up, a bulk of it is made up of water ice. And so in Beyond Earth, we envision a scenario where settlers on Titan could set up basically a factory where they dig up from the subsurface, and it's probably not that far into the surface, water ice, and convert that through electrolysis to oxygen and use that to burn the methane and other hydrocarbons that are so plentiful there. Another thing that I wanted to say about the desirability of Titan over Mars or other planets in the solar system for a human colony is just its Earth-like qualities. You know, we thought a lot about where would be a good place to set up a human colony in the solar system. And there's a lot of reasons to rule places out because they're too hot, too cold, not enough atmosphere, not enough gravity, and so forth. But there's also the aspect of how Earth-like a planet is. And Titan, surprisingly enough, is probably the most Earth-like planet or planetary body in the solar system. There's lakes on the surface. It's the only place in the solar system where there's liquid on the surface other than on Earth. Of course, it's not water, it's methane and ethane, but it lends an Earth-like quality to the surface. Again, there's the atmosphere that, as Charles mentioned, is mostly nitrogen, so we can't breathe it, but it is about 1.5 times the pressure on the surface as Earth's atmosphere. And so that gives you a lot of opportunities for movement through the atmosphere. You could fly if you wanted to, strap on some wings and fly. You could sail a boat across the lake. There's dunes there made up of hydrocarbons. So a lot of potentially pleasant aspects to living on Titan in terms of transportation and lifestyle. Even though it is cold and far from Earth, if you can overcome a few hurdles, there's a lot of good aspects to living on Titan.
Well, Charles, our early pioneers lived off the land by, of course, growing crops. Some people think that one day we'll grow crops on Mars because it has a carbon dioxide atmosphere, and perhaps we'll genetically engineer algae and stuff like that to live on Mars. However, Titan has no soil as we know it, no organic soil, plus it's very cold. There's no carbon dioxide for the plants to breathe, and so agriculture would be impossible on Titan, right? What are your thoughts?
No, I don't think it would be impossible. The agriculture would obviously have to be very different than it is here on Earth, partly whether on Mars or on Titan, because it would have to be done indoors. Both places are very much too cold for any kind of organic life that we know of. So you would have to create, you can think of it as greenhouses, but in fact, to have the productivity that you would need, you'd have to have some kind of algae generator or other high-tech bioengineered food system to provide enough sustenance, enough calories for a large society. But, the amount of time and technology advancement to get us out there, if that development is going on at the same time, it probably can be done. In terms of the gases that you would need, you've got everything there you need, and you can certainly create whatever atmospheric constituents you need from what's found on Titan in the abundant water and hydrocarbons. So I don't think that's overcomable, something that you can't overcome. But the advantages are so great of having protection from radiation and of having this energy source and of having the other resources you need to become self-sufficient that we think that, and we try to make the case in Beyond Earth, that if you want to consider a colony like, say, America, where people go and they don't need to be supported by the old country, in America, I guess it would be Europe, then you need to look to a place that has those resources and that ability for self-sufficiency.
Okay. Well, unfortunately, we have run out of time. But Charles, Amanda, thank you so much for being on Science Fantastic.
Thank you.
Thank you.
And once again, the book is called Beyond Earth, Our Path to a New Home in the Planets by Charles Walford and Amanda Hendricks. And you are listening to Science Fantastic with Professor Michio Kaku. Join us every week as we discuss the cutting edge of science and technology.
Science Fantastic with Sir Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because it's open mic. Let's take the first listener phone call.
Hey, this is Blake Steele from Chattanooga, Tennessee, calling from 102.3. I was just wondering, what exactly is radioactive material and...
Okay, well, we hear about radiation all the time, but the question is, what is radiation? Well, very briefly speaking, when you smash an atom apart, you break it apart, it's called an ion. But if you smash the nucleus at the very center of the atom apart, you get subatomic particles. And the fragments of atoms and subatomic particles are called radiation. Now, of course, there are many types of radiation because there are many constituents within the atom. The most common form of radiation is electromagnetic radiation. That is radio, television, visible light. All of that travels at the speed of light because that's what light is. Light is a form of electromagnetic radiation. X-rays, for example, are ionizing radiation, which can be potentially quite dangerous and give you cancer because it, in turn, can rip apart atoms. On the other hand, radio is non-ionizing. It does not have enough electromagnetic energy to rip apart the atom, so it is not as dangerous as X-rays. So that's one form of radiation. Then we have subatomic particles, alpha rays, beta rays. They're much more dangerous in certain ways. And they're found, for example, in fallout. If you have an atomic bomb, it releases an enormous amount of X-rays and other kinds of radiation, but it also makes radioactive dirt. So the dirt created by the hydrogen bomb that is lofted into the sky eventually rains down on the planet Earth in the form of radioactive byproducts. That is, atoms that have been ripped apart, which in turn release beta rays, which are electrons, and alpha rays, which are the nucleus of helium. Those potentially can be dangerous. They cause ionizing radiation, which can cause mutations. And mutations in turn can alter the very structure of life. And so we have a situation here where, yes, indeed, radiation can be dangerous, but we also have ways of controlling radiation as well. We have ways in which we can measure it, and we have shielding to protect us against radiation. But of course, sometimes it just gets out of control. Take a look at Chernobyl, take a look at 3 Mile Island, take a look at Fukushima. There we had reactors which literally blew their lid, like at Chernobyl, releasing all sorts of radioactive debris that eventually wound up in people's dinner table and in people's backyard. And so, once again, radiation can be dangerous, it can harm you, but also radiation can cure diseases, for example, radiation treatments if you have cancer, and the sun itself releases radiation which makes life possible. Sunlight is a form of radiation as well. Okay, well, moving right along, let's take the next listener phone call.
Hi, my name's Charlotte, and I'm from Bradford, New Hampshire. I'm calling to ask if insurance companies and employers are not permitted to discriminate against people with certain genomes that have been identified on the basis of disabilities or what have you. Then why is it that when we talk about children who might potentially be identified in the womb as having certain disabilities, genetic defects or markers, why is it that doctors are permitted to discriminate against these children?
Well, you ask an extremely important and touchy question, and unfortunately the law is not clear on these questions. However, let's break it down into its components. First of all, it costs about $500 to $1,000 to have all your genes sequenced. Personalized gene sequencing allows you to basically get all the genes that make up your body. Now, some of these genes are broken. They're mutated. They don't function properly. For example, for Caucasian people, they have to worry about cystic fibrosis. If you're African American, you have to worry about sickle cell anemia. If you're Jewish, you have to worry about Tay-Sachs. Each of these is caused by a mutation within our genes. So far, so good, right? But now we have the law coming into the picture, because as you know, laws have been passed to try to protect us against the predatory practices of insurance companies. They may want to kick you out, if you are predisposed to certain kinds of diseases. For example, Angelina Jolie, the movie star, made headlines recently when she had a double mastectomy because she was very likely to have breast cancer. She had the genes for breast cancer. The doctors told her that she had a very good chance of breast cancer. It ran in her family. So she had to make a decision to have a double mastectomy. But now you ask an even more delicate question: what happens in the womb? Now, for good or bad, it's possible to detect the genes that make up fetuses before they're born. For example, in Brooklyn, in New York, there's even a group of Orthodox Jews that make it possible to have the genome of the fetuses analyzed, and if the fetus has Tay-Sachs, then the parents, not the doctor, the parents have the option of not seeing that fetus to term. So in other words, no one's killing any fetus, but it does mean that parents have a choice. And again, it's not a question of a doctor discriminating against the unborn fetus. It's a question that the parents are given the option of not seeing that fetus to fruition, to birth, because of the fact that that fetus carries the genes for Tay-Sachs. Now, in principle, this may make it possible to eliminate Tay-Sachs in that family tree within just one generation, if everything goes well. Now, what about the possibility of the misuse of this technology? Well, there are two ways in which genes might be altered. First is somatic gene therapy, in which you simply repair the genes of an individual that's already been born. But there's also germline gene therapy. That is, changing the genes that make up the sperm and the egg, and thereby being able to control your entire genetic destiny forever. Okay? Now, many of the people who work in this frontier area say that somatic gene therapy might be okay, because of course you don't want to perpetuate suffering. For example, Huntington's syndrome. Huntington's disease is a horrible disease where you flail about like a wild person. Woody Guthrie had the gene for Huntington's. In fact, it's even suspected that one of the so-called witches of the famous Salem witch trial actually suffered from Huntington's. And that, of course, probably upset a lot of the neighbors who thought that maybe she was possessed by the devil or was a witch herself. But some people think that no, perhaps she just had a genetic disease called Huntington's. And so why not eliminate Huntington's disease from one generation? That's somatic gene therapy. But on the other hand, more controversial is germline gene therapy, where you alter your sperm and the egg so that your kids and your kids' kids and your kids' kids on forever have that gene eliminated. So once again, it's not a question of the doctor discriminating against certain individuals. First of all, it's a frontier area. The law has not made clear exactly what is possible and what is not possible. But in the best case scenario, it's the parents who have the option. That is, they're given a choice as to whether or not they should perform, whether or not they should see a certain fetus to term or not.
You're listening to Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, this hour is your hour. Okay, well, moving right along, let's take the next listener phone call.
Hello, Professor Michio Kaku. My name is Mike McCrow in Beaverton, Oregon, listening to you on station 970 in Portland. I was wondering, ancient lava flows have shown that the Earth's magnetic field, because of the alignment of iron, has changed polarity from north to south several times in the history of the world, of the Earth. I was wondering, when this happens, what effect will that have on the Earth's magnetic field and its ability to prevent harm from the solar rays? Thank you.
Well, you ask a very thoughtful question, and you're absolutely right. If you go to, for example, Hawaii or any place where you've had multiple lava flows, and simply dig right into the lava flows and calculate the direction of the magnetic field, which is very easy to do because you have iron crystals inside the lava, and when the lava freezes, the direction of the North Pole is frozen in the lava. And as the next lava flow comes, the Earth's magnetic field has changed, and you can actually see the direction of the magnetic field changing in direction as you dig deeper and deeper into the crust of the Earth. And then the question is, are we headed for another one? And the answer is yes. We have records going back hundreds of years of the strength of the magnetic field of the planet Earth. Not, of course, scientific, but enough that we scientists can thereby recreate the strength of the magnetic field going back centuries. And yes, indeed, we are due for another change because the North Pole, the magnetic North Pole, does tend to wander. Now, I have to, at this point, make a very strong statement. I'm talking about the magnetic north. I'm not talking about the geologic North Pole. What's the difference? Well, the magnetic North Pole can wobble. It can change because of the fact that there are different kinds of currents inside the Earth which give us the magnetic field. But the geologic North Pole wobbles only slightly. In fact, we think that's where the ice ages come from. Very tiny wobblings of the geologic North Pole affects the amount of sunlight we get over hundreds of thousands of years, and that influences the ice age. But they're different. So when I talk about a pole shift that is going to come in the next few hundred to 1,000 years, I'm not talking about a geologic pole shift, which would, of course, destroy much of life on the Earth. It would disrupt the oceans, the continents, set off earthquakes, and all sorts of stuff. If you saw some of the movies that Hollywood has created concerning Armageddon and Doomsday, you know what could happen if the geologic North Pole were to change. Now, the caller asked a different question, a more thoughtful question, and that is, what happens if the magnetic North Pole does continue to decrease in intensity and finally flip? Is it the end of the world? No. It's happened many times in the past. And after the break, we're going to talk about a planet that did have a magnetic field which was reduced to zero with catastrophic implications. That is the planet Mars. Okay, let's take a short commercial break.
You're listening to Science Fantastic with Professor Michio Kaku.
Here is Professor Michio Kaku. Welcome back to Science Fantastic with Professor Michio Kaku once again. Well, before the break, we had a caller calling in a rather thoughtful question stating that, well, yes, the magnetic field of the Earth is gradually changing, and in the coming centuries to millennia, there could even be a pole shift. And is that dangerous for life on the Earth? Well, yes and no. First of all, we're not talking about a catastrophic shift of the geologic North Pole, which would, of course, split the Earth and create all sorts of havoc. We're talking about a change in the magnetic North Pole, which happens every few tens of or hundreds of thousands of years. It has happened multiple times in the past. Now, we need a magnetic field to protect us against solar flares and the radiation coming from the sun. Now, Mars has almost no magnetic field to speak of. Therefore, without a magnetic field to protect it against the sun's harmful rays, it means that Mars is continually bathed by radiation from solar flares. As a consequence, that's why Mars has almost no atmosphere to speak of. The atmospheric density is only 1% that of the planet Earth. So it means that if you were to take off your spacesuit on Mars, you'd suffocate, and the pressure being so low, eventually your face would actually explode as a consequence. So we, on the other hand, have an Earth with a very large magnetic field. That magnetic field sets up a shield that protects us from the harmful radiation from the sun. And that's why we have a very rich atmosphere on the planet Earth. Then the caller asked the question, well, if we do have another pole shift, which has happened in the past, what does it mean for life on the Earth? How dangerous it is? Well, it'll be dangerous because solar radiation will be bathing the Earth. But hey, look, it's happened before. We got through it. It may mean, for example, that life hundreds, thousands of years from now may have to go underground. We may have to temporarily live in underground shelters or cover ourselves to protect ourselves from the ultraviolet radiation from the sun, but it doesn't mean the end of the world. So no one's predicting the end of the world, even if we have a change in the magnetic North Pole of the planet Earth. It's happened before, and we got through it, and the strength of the magnetic field of the planet Earth is decreasing. We can actually measure that. We don't know when there may be a potential pole shift or a shift of the magnetic North Pole, but we are talking about something that will happen on a scale of centuries to millennia. In other words, don't hold your breath. Okay, well, let's move right on to the next listener phone call.
Hello, Professor. I was just wondering, I heard you're talking about the universe accelerating. My name is Nathan. I'm calling from West Virginia. And was wondering your thoughts on the universe accelerating, because at the far edges of the universe, the unknown area has mass. If it has mass and it has gravity, therefore it's pulling the universe towards itself. Thank you.
Okay, well, I think what you're asking is, well, first of all, the universe is accelerating in its expansion. It's not slowing down like we originally thought. It's actually speeding up. And perhaps the reason for the speed up is, well, maybe there's a gigantic object way out there, an object that is so large that it is tugging on us, giving us the false impression that the expansion of the universe is accelerating, when actually it's only due to the presence of a nearby but very, very massive object. Well, that theory cannot be ruled out. However, it does not agree with the data today. In fact, let's take a short commercial break, and I'll talk about the data today, about exactly what is the large-scale structure of the universe.
You're listening to Science Fantastic with Professor Michio Kaku. You're listening listening to Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Well, before the break, we had a call. Yes, indeed, the universe is expanding. Everywhere we look, we see that not only are the galaxies moving away from us, but the farther they are, the faster they're moving. And we once thought that the acceleration was slowing down. Now we realize that it's actually speeding up. And that leaves us with the possibility that maybe one day we'll be headed for a big freeze. The universe will be so cold that even life itself cannot survive. All life will die when the universe itself freezes at absolute zero. Well, at this point, I advocate, and other scientists have discussed it, maybe we should leave the universe. Maybe we should leave the universe and create an interdimensional lifeboat and sail to another nearby universe where it's warmer, and perhaps we can mess up that universe as well as messing up this universe as well. Well, the caller asked a question. Is there a gigantic object out there that is tugging on us? Or that is the origin of this acceleration? And the answer we think is no, because everywhere we look, the universe seems to be uniform. In fact, it is uniform almost to a mathematical precision. When we measure the background radiation that fills up the universe, the remnant of the Big Bang itself, we find that it is remarkably uniform. So whatever explosion created a universe that is uniquely uniform. In other words, there is no large object out there tugging on us that we are aware of. However, the latest theory is called inflation, and inflation does leave the possibility that maybe the universe could be lumpier than we thought. Perhaps in our sector of the universe we had a cosmic explosion, but maybe, just maybe, Big Bangs happen all the time. Even as you're listening to this radio program, perhaps universes are being created. If that's true, it means like a balloon inflating, there are tiny sub-balloons that are peeling off, and they are also inflating, and that creates a rather lumpy structure. But in all these balloons, in all these bubbles, the universe is still uniform within each bubble, and the universe is either accelerating or even contracting. That's called inflationary theory. It's gotten a lot of publicity. In fact, we had the originator of the inflationary theory, Professor Alan Guth of MIT, on Science Fantastic. He may eventually win the Nobel Prize in Physics for giving us perhaps the most accurate, realistic model of how the Big Bang took place, which in turn predicts there could be other Big Bangs happening all the time. Okay, well, moving right along, let's take the next listener phone call.
Yes, Professor Michio. My name is Ron, and I'm in Nikiski, Alaska. I'm just curious. I've watched a show on the History Channel about a guy who actually had a concrete building. He made his own little township. This guy defied gravity, but they didn't know exactly how he did it. He lifted blocks by using something natural that would weigh in the tons with no machinery, anything. And I just, curiosity-wise, what would you think of how this guy even accomplished that?
Okay, well, we'll have to take a short commercial break, but after the break, we're going to talk about anti-gravity. Can you really levitate?
You're listening to Science Fantastic with Professor Michio Kaku. Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku on Science Fantastic. It's open mic. Well, where we last left off, we had a caller calling in about something that's quite exotic, but it's a question that I often get, and that is, what about anti-gravity? Throughout history, there have been a number of reports, some of them rather convincing, that seem to indicate that people can literally defy gravity. Think of it, people that climb ropes, Jack and the Beanstalk-like, and go to heaven simply by levitating. In fact, the transcendentalists even have a photograph of some of their people meditating, and there they are hovering above the floor. Unfortunately, when people ask to have a demonstration of this in a scientific laboratory, they have demurred. But let me say a few things about what science says about anti-gravity. First of all, the science as we know it, that is quantum physics and relativity, which are the two leading theories of the universe, they do not allow anti-gravity. I repeat, N-O. So it means that all the tricks that you've seen in magic shows and stuff like that are exactly that, tricks. However, when you go to the very edges of science now, then you're talking about, well, there are caveats, there are footnotes that you have to add to Newton's laws of gravity, Einstein's laws, and the quantum theory. First of all, if there's something called negative matter, that is the opposite of matter. Not antimatter, but negative matter. Negative matter would fall up. It would have anti-gravitational properties, but we see no evidence of it. In fact, if there was negative matter on the Earth billions of years ago, it would have literally floated away. Now, why are we physicists interested in negative matter? Because if you have enough negative matter, you could violate so many laws of Einstein that you could have a time machine. That's right, a wormhole machine, a time machine, warp drive. All the stuff you see in Star Trek would be possible if we had large quantities of negative matter. Now, to be frank, we see no evidence, I repeat, no evidence whatsoever of negative matter. All I'm saying is that if negative matter did exist, it would break Einstein's laws in a very precise way, such that things would float, things would fall up, not down, that you could get levitation. And if you have enough of it, it would actually warp Einstein's equations so much that it would allow for time travel and warp drive and pretty much everything you see on Star Trek. There's also yet another way of creating anti-gravity, and that is the fact that the universe seems to be accelerating. In fact, the Nobel Prize was given to 3 astronomers a few years ago for this astounding discovery that the universe is not slowing down in its expansion, it's actually accelerating, careening out of control. This means that something is pushing the galaxies apart, and we think that it is dark energy, the energy of nothing. Even nothingness has energy as predicted by Einstein's equations, and perhaps that's the reason why we have an accelerating universe. Well, that creates anti-gravity, because anti-gravity is pushing the galaxies apart. However, to be fair, I have to say that the amount of anti-gravity pushing the galaxies apart is minuscule. Tiny, so small you cannot build a time machine out of it, so small that it's of no practical use whatsoever. We do know that between galaxies, however, there's enough of it so that you can, in fact, push the galaxies apart. So that is a form of anti-gravity that we think can exist, but it is extremely tiny. You're not going to be able to levitate off the floor using this kind of technology. So anyway, just to repeat, anti-gravity as seen in science fiction movies is not possible using the known laws of Newton, Einstein, and the quantum theory. However, there are fuzzy areas. If you have negative matter, which we've never seen before, then perhaps anti-gravity is possible. But, well, don't hold your breath. We have yet to find any evidence whatsoever of negative matter. Okay, well, I think there's time maybe for one more listener phone call. Let's take the next listener phone call.
Hello, my name is Verl Potter. I live in Richland, Washington. I listen to you every Sunday night from 8 to 10 p.m. on radio station KONA. It's Kona, which is 610 on the radio. My question is, I heard that all the planets rotate counterclockwise, including Earth, except one, Venus. Someone told me that Venus is the only planet that rotates all the planets rotate counterclockwise. And I was told that Venus is the only planet that rotates clockwise. Why is that? I was just curious. Thank you. Okay, bye now.
Well, you're absolutely right. Venus is an oddball. But first of all, let's describe the solar system itself. We have the sun, of course, at the center, and then we have a disk called the ecliptic plane, a disk that surrounds the sun, and all the planets lie along this disk. Now, inside this disk, all the planets go around the sun in the same direction. I repeat, all the planets go around the sun in the same direction. However, inside each planet, they have their own spin. And if you take a look at the spin of the planet, we find that Venus actually spins in the opposite direction. So, in other words, all the planets move in the same direction around the sun in this disk called the ecliptic plane. But inside the ecliptic plane, each planet spins on its own axis. And if you take a look at the Earth, Mars, and Mercury, we find that its spin is in the same direction, but Venus goes backwards. And why is that? We think there probably was a cosmic collision. A cosmic collision when the solar system itself was first formed 4.5 billion years ago. And these cosmic collisions created the bizarre shape of the solar system. Where did our moon come from? From a cosmic collision with an asteroid about the size of Mars. But in the form of Venus, we think that a collision took place which reversed the spin of Venus. Well, unfortunately, that's it for Science Fantastic.
Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, we're going to throw the lines once again because this hour belongs to you. Well, let's move right along and take the next listener phone call.
So obviously planets and stars are very far away. So my question comes to you as, would you say that the bigger problem to getting to the stars and planets comes from the sheer distance away from Earth that they are, or the fact that since they are so far away, that we just don't have enough fuel to get there in the first place?
Well, the answer to your question is actually yes for both. The reason why we cannot go to the stars anytime soon is because, A, they're very far away, and to get there requires an enormous amount of fuel. For example, let's take the Saturn rocket. The Saturn rocket went to the moon in 3 days, and it was the biggest rocket ever created by the human race. And if the rocket were to go to the stars, how long would it take? It would take the Saturn rocket 70,000 years. I repeat, about 70,000 years for it to just make it to the nearest stars. So obviously, chemical rockets are not the way to go. Chemical rockets are simply too feeble. No matter how powerful they may look on national television, blasting off from Cape Canaveral, they are puny compared to the enormous distances involved with the universe. So how are we going to get to the stars? Well, in my book, Physics of the Impossible, I lay out what the designs are for starships. One is to use fusion power. This is called the ramjet fusion engine. It's basically a gigantic ice cream cone in outer space. It scoops up hydrogen in the forward direction as it moves, burns it, fuses it in its chamber, and then spews out gas and exhaust on the other end. And so the fuel supply is limitless because it scoops up interstellar hydrogen, and there's basically an infinite amount of interstellar hydrogen out there. And so that's one way to do it, the ramjet fusion engine. The only problem is that we have not yet attained fusion on the planet Earth for peaceful purposes, let alone for star travel. The next possibility is antimatter rockets, just a la Star Trek. If you watch Star Trek, they always talk about impulse power from the antimatter engines. That sounds great, antimatter gives you total conversion of matter into energy via Einstein's famous equation, E equals mc squared. So what's the catch? There's always a catch someplace. The catch is antimatter, even though it does exist, is extremely expensive to make. The only way known of making antimatter on demand is with an atom smasher. And think about that. The atom smasher we have in Geneva, Switzerland, the Large Hadron Collider, is only a fraction of the energy necessary to go to the stars. In fact, it is a quadrillion times too small to create enough fuel to take us to the stars. Now, another proposal was highlighted by Stephen Hawking, my colleague, just a few months ago, and that is, why not use solar sails energized by laser beams to blast postage-size starships to the stars? Now, we've been brainwashed by Star Trek. We've been brainwashed into thinking that a starship has to be the size of a battleship, like the Enterprise. The Enterprise is huge on that TV program. Well, why not send a postage stamp chock full of computer technology, cameras, recorders, receivers, transmitters? Why not send a postage stamp, because of modern electronics we can do this, and put it on a sail. The sail is perhaps no more than the size of several feet, and then use laser beams on the Earth to shove these postage-sized sails into outer space. That means you wouldn't have to have any rocket fuel. The rocket fuel, if any, is actually on the Earth in the form of what energizes the laser beams. And so with laser beams powerful enough, you can actually send these things out to Alpha Centauri at about a fifth of the speed of light. In about 5 years, think about it, you can reach Alpha Centauri, the nearest star. Now you may say to yourself, hey, that's really neat. Why not send a postage stamp computer to the nearest stars? Well, what's the catch? There's always a catch someplace. And the catch here is that the laser beam necessary to energize this would have to have the energy of 100 megawatts of power. That's 100 nuclear power plants. So think of 100 nuclear power plants, all energized to shoot a laser beam to unfurl a sail in outer space that carries a postage stamp to the nearby satellites at a fifth of the speed of light. Well, each nuclear power plant in turn costs about $2 to $5 billion, and you need 100 of them. So you very quickly see what the problem is. The problem is cost. We got to bring the cost down. In fact, much of the problems with building these starships is cost. Antimatter is very expensive. It costs a lot of money to build 100 nuclear power plants. And so we're not going to go to the stars anytime soon. However, I say perhaps in a century with the falling of prices, we may be able to send the first Starship to the stars. Okay, well, moving right along, let's take the next listener phone call.
Hello, Professor Michio Kaku. This is Paul Smith from Vancouver, British Columbia, Canada. And my question is a concern I have regarding the Fukushima disaster. Now, I'm wondering if the fuel rods or the pellets have breached the containment vessels, where is that fuel? Is it possible that it goes into the earth, actually melting through layers of rock and maybe going right to the other side of the earth? Do we know anything about this? And building 4, if it's going to blow, is this not the worst environmental disaster the earth has ever seen, far beyond Chernobyl? Look forward to hearing an answer from you. Thank you. Bye.
Well, just recently we passed the 5th year anniversary of that horrible nuclear power plant accident, and it was time to, think about the future of nuclear energy given the enormous problems caused by that accident. First of all, we know more or less the state of the reactor. We had 3 full-scale meltdowns. 3 full-scale meltdowns. In fact, the cores of all 3 actually liquefied. We've never seen this before. Even at Chernobyl, even at 3 Mile Island, we did not have a complete liquefaction of the cores, but that's actually what happened at Chernobyl. Now, what happens when the core goes through the Earth? Well, there is something called the China Syndrome. It's a movie, but it's also slang in the nuclear business that if you have a meltdown, perhaps the hot core will melt right through the floor of the reactor, right through the bedrock of the Earth, right through the center of the Earth, and go all the way to China, and that's what's called the China Syndrome. Well, you're not going to get the China Syndrome. However, we do have computer simulations of full-scale meltdowns. They're called Class 9 simulations. We do know that you're not going to melt all the way to China. However, you will melt right through the bottom of the containment vessel onto the floor of the reactor. At that point, you will have a steam explosion capable of blowing the lid right off the reactor. And that's what happened at Chernobyl. Chernobyl, we had a steam explosion and a hydrogen gas explosion which blew the lid off the reactor. If you calculate the total amount of inventory that was released into the environment, roughly 20% of the core at Chernobyl was essentially vaporized and shot into the atmosphere, creating havoc in the area around Kiev. Now, it turns out that the Fukushima disaster did not release that much radiation into the atmosphere because a lot of it was still contained within the structure at Fukushima. However, we do not know the state of the core. The core is in liquefied form. It has since perhaps resolidified. Submarines have been sent into the bottom of the reactor to try to take photographs of the melted core. They were unsuccessful. So believe it or not, we are going blind. We do not yet know what the state of the core is. The accident is still in progress. Think about that. Just like Chernobyl. The Chernobyl accident is also in progress. How did the Russians stop this raging reactor fire back in 1986? Believe it or not, they did it with the Red Air Force. The Air Force was called in. They sandbagged the reactor by dumping borated sand and borated liquid on the burning reactor. They basically entombed it in concrete, and therefore the accident is still in progress.
This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. This hour is your hour. This is the time when you can give us a call and get on national radio. Well, really briefly, where we last left off, we were talking about the Fukushima and Chernobyl disasters, which are still going on. Even though that Chernobyl accident took place so many years ago, it turns out the core has been sandbagged, entombed in concrete, but it is still melting. Not the China, but it is still melting right through the floor of the reactor, and we still do not have a permanent way to stop the core from continuing to melt into the Earth. One possibility is to dig a tunnel underneath the Chernobyl accident, and then reinforce it by creating a pan underneath the core to prevent the core from melting any further into the Earth. At Fukushima, we have a situation where we have 3 melted cores that are continuing to melt, and we don't even know what the configuration looks like. In fact, the Fukushima disaster is still not under control at all. Robots have been sent in because it's too radioactive for ordinary workers to work more than just a few minutes, and each time the robots have failed to carry out their primary missions of bringing the accident under control. And so the short story is both accidents are still in progress. They have to be monitored very carefully because who knows, maybe another steam explosion could rip the reactor apart and the accident starts all over again. Stay tuned. Okay, well, moving right along, let's take the next listener phone call.
Stephen Hawking recently elaborated on his previous ideas that black holes can remove information from the universe. What does Stephen Hawking mean when he says that black holes are removing information from the universe?
Okay, well, you ask a question which is at the cutting edge of modern physics. In fact, if you can find the answer to this problem, you may win the Nobel Prize in physics. Well, everybody knows, even children know, that when something goes into a black hole, it doesn't come back out again. In other words, a black hole is a cosmic roach motel. Everything checks in, nothing checks out. Now, if you have the Encyclopedia Britannica and you throw the Britannica into the black hole, it's lost forever. The Britannica never comes out again. But you see, there's a problem there, because that violates quantum mechanics, which we think is the ultimate law of the atom and atomic physics. In quantum mechanics, it turns out that information is never lost. Now, you may say to yourself, now wait a minute, if I burn the Britannica, isn't the information of the Britannica lost, even under ordinary chemistry, when I burn it? And the answer is no, because in principle, you can move all the molecules backwards in time, run the videotape backwards, and so all the fumes and the flames disappear, and you get back the Encyclopedia Britannica. Now, of course, to do that would stretch the imagination, but in principle, because that's what quantum mechanics says, in principle, it is possible to hit the reverse button and have the Britannica unburn and reform as the Encyclopedia Britannica. Now, black holes are different, because you can't run the videotape backwards, because nothing comes out of a black hole. And so the thinking was, as Stephen Hawking said, black holes must violate quantum mechanics. Information is lost forever. Well, I work on something called string theory, which is a quantum mechanical theory, but it also embraces all of Einstein's theory. In fact, we think it is the theory of everything. It contains both atomic physics, the theory of the atom, as well as relativity, the theory of the universe itself. And quantum mechanics says that information is never lost. In principle, you can always run the videotape backwards. But if nothing can get out of a black hole, where did the radiation go? Where did the information come from? Well, you see, black holes are not entirely black. It was Hawking himself who said that black holes are actually gray. They seep out tiny quantities of radiation, and that's where we think the information is. If you can retrace all the photons coming out of a black hole, which we cannot do in practice, we can recreate the Encyclopedia Britannica. So Hawking admitted defeat. String theory, score 1 for string theory, score 0 for Stephen Hawking on this question.
You're listening to Science Fantastic. Here is Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Okay, well, let's move right along and take the next listener phone call.
Hi, Dr. Kaku. This is Brendan Mayhew. I was just calling to get a little insight on what the big crunch is and what might happen in that scenario and what might happen after that. All right, thank you for your time.
Well, many years ago, when I was first learning about cosmology, I learned that according to Einstein, there were 3 possible futures for the distant universe. One possibility is that after the Big Bang, the universe just keeps on expanding and gets colder and colder, and that's called the Big Freeze. The Big Freeze is when the universe, it just keeps on expanding, doesn't stop at all, and it gets colder and colder, and will all basically freeze to death. That's the Big Freeze. The other possibility was the expansion of the universe could stop and reverse itself. And then the distant galaxies would come closer and closer to the planet Earth. And instead of getting colder, it would get hotter. The galaxies would come closer to the Earth. And when you look at the night sky would become totally white because of all the stars and galaxies that are rushing toward the Earth. In fact, it would get so hot that perhaps there could be another explosion, and perhaps we would get what is called the cyclic or oscillating universe. And the third possibility is that we're somewhere in between the two, but it would still last forever, the expansion. Well, now we have satellite data. And we now have proof that the universe is not only expanding, but it is accelerating. We once thought that the universe was slowing down, but no, it's actually accelerating. So at the present time, the leading possibility for the future of the universe is the big freeze rather than the big crunch. But we don't know why it's happening. There's something we think called dark energy. We're not positive, but something we think that's called dark energy that is pushing the galaxies apart, giving us the expanding universe. But if it's pushing all the galaxies apart, then what is it? Well, according to Einstein's theory, it is the energy of nothing. Even nothingness has energy associated with it. But how much nothingness and how much energy is there in the universe? We don't know. Now, string theory actually does explain this, the accelerating universe, but cannot give you a prediction for the amount of acceleration. So at the present time, we really don't know what's causing the accelerating universe. If you ever find out, you'll win the Nobel Prize in Physics.
You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, you are listening to Science Fantastic, and it's open mic in this hour. Okay, well, moving right along, let's take the next listener phone call.
Hi, my question is, in this day and age, why are scientists still so apprehensive to look into the possibility of alien life?
Well, I'll be blunt. Many of my colleagues suffer from something called the giggle factor. And that is, anytime you mention UFOs or Bigfoot or Loch Ness Monster or whatever, they giggle. Their eyes rolled up into the heavens and they sort of chuckle and laugh. Well, I don't laugh because that's not a very scientific approach to the question. However, there are legitimate concerns about whether or not alien life can exist in outer space. First of all, let me say that my own personal point of view is that yes, they are out there. We can debate, however, as to whether or not they've actually landed on the Earth or can go between these cosmic distances between stars. But yeah, I think there's so many galaxies out there, so many stars, and so many planets that we've identified that are Earth-like. We've taken a census of the Milky Way galaxy with the Kepler satellite. We think that perhaps roughly 1/10 or perhaps 1/20th of the stars out there seem to have planets going around them that could harbor life. In fact, the latest number that I've seen in the literature is about 1 billion. About 1 billion Earth-like planets in our own backyard. And to assume that we're the only game in town, I think, is a little bit presumptuous. However, to be fair, the critics of this theory would say that, well, there's a problem, and that is the distance between stars is so great that we don't think that they're going to reach us anytime soon. Well, yeah, it would take about 70,000 years for a Saturn V rocket to reach the Earth, but that assumes that they're going to use Saturn V fuels, that is, chemical rockets. I mean, after all, if they're not 100, but if they're 1,000, if they're 10,000, 1,000,000 years ahead of us, then whole new laws of physics begin to open up for them that we can only dream about at the present time. So in other words, the critics are right that with technology maybe 100 years more advanced than ours, we're simply not going to see aliens darting across the night sky. However, if aliens are perhaps millennia ahead of us, then there is a possibility. And we physicists actually rank extraterrestrial civilizations rather than talk about aliens in outer space. We actually rank them into type 1, type 2, type 3. A type 1 alien civilization would have the power of an entire planet. They would be planetary. They would, for example, control the weather. They would have enormous amounts of energy because they have the resources of an entire planet, sort of like Buck Rogers or Flash Gordon. Then there's type 2. They have stellar energy, the energy of an entire star. They play with stars like Star Trek. The Federation of Planets would be a typical type 2 civilization. And then there's type 3. Galactic. They roam the galactic space lanes. They play with black holes. And that's type 3, like the Empire of The Empire Strikes Back. So you see, on this cosmic scale, you see that we are type 0. And of course, a type 0 civilization like ours is not going to be able to go to the stars. And of course, a civilization that's only 100 years ahead of us will also not be able to reach the stars. But if you are a full-blown type 1 civilization, you could be hundreds of years more advanced than us. A type 2 civilization would be a few thousand years ahead. Type 3 would be perhaps 100,000 to 1,000,000 years ahead of us. And on that time scale, you have to open your mind to the possibility of new laws of physics opening up to aliens from outer space.
Yes, Professor Kaku can help you with your homework. He can even help you with your kids' homework, but only if you ask. You're listening to Science Fantastic with Professor Michio Kaku. Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open in this hour. Okay, so moving right along, let's take the next listener phone call.
I don't understand why we focus so much on expanding our horizons into the universe. I think that we should actually focus on expanding our horizons within our own life and the atoms and the molecules. Why hasn't anybody discovered something within molecules that we don't currently know? Let's not build telescopes to look toward the skies. Let's build telescopes, microscopes, to look towards the atoms. Why haven't we done that?
Well, the simple answer is that we have done it on a limited scale. First of all, we have electron microscopes where we use electrons. Electrons vibrate according to quantum mechanics, and as a consequence of the vibration, they can be used just like optics, just like photons vibrate, and we can use the vibration of photons to see objects in space. We can use the vibration of electrons, and the electron wavelength can be much smaller, and so we can actually see things on a much smaller scale than we can with a ordinary microscope. Well, if that's true, then why not use more subatomic particles to get even smaller? Well, you can, and they're called particle accelerators. So we actually do have instruments that can peer into the very heart of an atom, and these are the particle accelerators. So they, in turn, can reach down to distances much smaller than a proton. About a fraction of the size of a proton is the distance that we can probe with our atom smashers. The largest atom smasher is in Switzerland. It is the Large Hadron Collider. It found, for example, the Higgs boson just last year, and we think that there are more subatomic particles that we hope to find. So yes, there is something like a telescope that can see even smaller than a proton, and that is particle accelerators. However, of course, to be fair, you're not going to get those fantastic pictures that we do get with optical telescopes and with electron microscopes. When you peer down at that scale, ordinary pictures become impossible. However, you can detect the presence of particles at that small distance, but you're not going to get glorious photographs of the inside of the atom. And that's because at that distance, everything obeys the Heisenberg uncertainty principle. Everything becomes fuzzy at these distances. distances, and so you're not going to get glorious photographs. But you will be able to detect the presence of subatomic particles like the God particle, otherwise known as the Higgs boson. That we can do. Okay, well, let's take the next listener phone call.
Hi, my name is Corey Ross Robertson. So I am wondering regarding colonizing the universe. So I'm familiar with the Drake equation. I know one of the variables in the Drake equation is the likelihood that a civilization will survive long enough to allow for the civilization to develop enough to colonize other planets and utilize space travel. Given our planet's history and our civilization's history, what do you think the likelihood is of our civilization being able to overcome our destructive ways in order to last long enough to colonize other planets like Mars and even further outside of our solar system? Thank you. Have a nice day. Bye.
Okay, well, you asked several questions in one, so let's try to break them down to their components. First of all, you mentioned the Drake equation. Frank Drake was an astronomer back in the 50s who tried to estimate the number of intelligent civilizations there are in the galaxy. And the equation he came up with is not unreasonable, and we still use it today. First, you start with the total number of stars in the galaxy. We know that number. It's about 100 billion stars in the galaxy. And then you reduce that systematically. You reduce them, first of all, to the stars that are like our sun. So maybe half the stars in the galaxy are somewhat similar to our sun. And then a fraction of them have planets going around them. A fraction of those planets have liquid oceans and are potentially habitable. A fraction of them may have microbial life. A fraction of them may even have large complex life forms. A fraction of them may even have intelligent civilizations. And the last factor in the equation is a certain fraction of these civilizations are long-lived. So they live long enough for us to detect them. In other words, they're not a flash in the pan. They're not going to simply blossom and then blow themselves up with nuclear weapons or biogerms or what have you. They're going to live long enough for us to detect their presence. Now, as you can see, there are a lot of variables in this Drake equation. However, now we have the Kepler satellite. We can actually answer many of the parts of the Drake equation. And the revised Drake equation that we now have because of the Kepler satellite, which can detect planets in outer space, is that perhaps a billion planets orbit stars that are Earth-like. And however, there are still unknowns of the billion planets that are Earth-like. We still don't know what fraction of them have oceans, what fraction of them have microbial life, what fraction of them have intelligent life. But we're beginning to fill those gaps. However, you ask yet another question. And the last question is, of these civilizations that emerge from the swamp, how many of them don't blow themselves up? And of course, that is a big question for which we do not have an answer. Let me say that however, we are on the brink of mastering weaponry technology that can easily wipe out all life on Earth. And so it's not clear at all. It's not clear at all whether we will be able to tame these cosmic forces or whether these forces will blow ourselves up. Maybe when we go to the stars and visit planets, maybe we'll visit planets that are lifeless, that had a runaway greenhouse effect, that have radioactive atmospheres because of a nuclear war. We simply don't know the last factor in the Drake equation, and that is, are we nothing but a flash in the pan, or will we commit cosmic suicide? Okay, well, unfortunately, that's it for Science Fantastic. Good day.
You're listening to Science Fantastic.